This example is the cable that is subjected to a uniformly distributed load, and we are going to determine the force at point A, force at point B, the force at point C, and the radius of the cable. Let us first start by take a look at the cable that we have. The cable subjected to this force distributed along the length of this very stiff girder. That means this girder will not deform at all. So it's when it's pulled, it's going to pull down at the same level. So you may model this distributed load like this, and then you said this one is 850 kilonewton per meter, and then this force transfer from the girder across the anchor, okay, anchor, and then since the anchor is in the vertical direction, so it's directly transferred uniform loading to the cable, and the cable supported by the pin. So the pin gonna have the reaction, and the reaction that we have is gonna be A sub x, A sub y, and C sub y, and C sub x. Okay. Next, you may see the point B is the lowest point of this cable, and if you set the origin of the coordinate x and y here, you will have the coordinate here of 0, 0. And to do this, you got to consider the cable equation. Okay, the cable equation that we have is in the form of y equal to w, we know w already, divided by 2 f sub h, and then times x square. So we got to define what is this. The y is going to be the vertical, okay, direction, and the x is going to be the corresponding horizontal direction. By doing this, if you move this one to point C, and if you set this to be the x, okay, then this one, this portion, going to be 100 minus x. And how do we find the f sub h? Anyway, to solve this kind of equation, we got to use the no coordinate. What is going to be the no coordinate? If you move from the B horizontally to the C and up, it's going to have the coordinate of x and 20. Okay, and if you move this direction, it's going to be 100 minus x, and you move up, the coordinate is going to be 100 minus x. However, since it's in negative, it's going to be minus, and then this y is 40. You get the coordinate of A like that. To solve the cable equation, then it is in the parabolic equation, we got to use the boundary condition, okay, by using the cable boundary condition at A and C. Okay, we can find the position of b or x. Okay, let us consider at point A. At A we have the coordinate there of minus 100 minus x and 40 meter. So if we put the y here, it's going to be 40, and then equal to this one is 850 divided by 2, and then we don't know it yet, f sub h, and the x is going to be this, and since it's x square, so this is can be 100 minus x, x, and then square. This is going to be our first equation. And then if you further consider at point C, your equation going to be what? At C here is going to be 20, okay, equal to W 850 divided by 2 and f sub h, and then that is going to times x squared. Okay, and if you further consider these two equations, you can see this part of equation are the same. So you may rewrite this equation again, and you may get this one to be 40 and divided by minus x, okay, and then square, and this is going to equal to 850 divided by 2 f sub h, and this one also, if you write this, it's going to be 20 divided by x squared. This one going to equal to 850 divided by 2 f sub h. And then if you put them together, you may get the equation of 20 divided by x squared, and that's going to be equal to 40 divided by what? Divided by 100 minus x and square. And then to solve this, you got to what? Move this one up, move this one up. So the equation can be 20 times what? Times 100 minus x and square, and equal to 40 x squared. And then if you expand this equation, okay, you may get this one 20 times 100 squared minus 2 times 100 times x, and then plus x squared. That is going to be 40 x squared. If you rearrange this equation to be the proper format, you may get this one of x squared plus 200x and minus 10,000, and then equal to 0. How can you solve this equation? If you use the Cartesian algebra, you can solve it directly. If not, you need to go back to the equation. The x gonna be minus b plus minus square root b squared minus 4ac over a. Okay, and now if you do that, you may get the x equal to 41.42 meter, and the other one is going to be minus 241.42. So you got two results. and which one going to be the proper one. And you can see we have the length of 100 meter. So this should not be our result because it's larger than 100. So the result gonna be this one, the x. If x is equal to 41.42, you may come here. That is going to be equal to 41.42 meter. And if this one is 41.42, this one could be 100 minus 41.42. That is going to be 58.58 meter. So we get the location of point B now. And we also has the equation for this cable. So what is going to be the equation of this cable? We will not know yet until we find f sub h. To know this equation, so we got to select. If we put x, okay, into this equation, you can see, if you put 41.42 here, you can solve for f sub h. So based on this equation, you may put f sub h up. Find the force f sub h. Okay, you put the f sub h up, and then this is gonna equal to 850 divided by 2, and this is up, this is down, times 20, and the x is going to be 41 point, this is going to be 41.42, and this is also square. If you put this in your calculator, you will get your f sub h of 36,456.9 kilonewton. So that is going to be the horizontal force. And if you may recall from what we discussed before, this is going to be the f sub h, because f sub h is all equal no matter the point of the cable is. This is the horizontal force. So you obtain this force of 36,456.9. And now we are ready to write the cable equation. The cable equation is going to be what? Y equal to, this is going to be 850 divided by 2 and times 36,456.9, and then it's gonna times x square. And if you put everything together, you will get this to be what? To be 0.0116,576 and x square. This is gonna be the equation for the cable. The cable equation is this one. So now you can plot the shape of the cable following this. Okay, the shape of the cable will follow this equation. And also you can find the slope of the cable by doing this, just the slope. Slope is going to be dy by dx. Okay, if you dip this, you're going to get this one to be 0.02, 2 times of that, 0.33152 and times x. Okay, that is going to be also equal to tan theta. That equation will be used later to determine the slope and the angle at any point of the cable, and then we also can use the horizontal force to determine the force of any point of the structure. Okay, next we come back to consider the cable again. We are going to find the force T sub A. That means the force here. The force here is supposed to be the tension, something like this. It's the projection of this one and projection of this one. And also the force T sub C is here. Okay, it's going to be the projection of this one and projection of this one. And as you may notice, if we know the slope here, we can find the relationship between T sub C and C sub X, because we know this already. Let's see, this one is going to be theta sub C. If this is theta sub C, okay, you may see that this is going to be T sub C and cosine of what? Cosine of theta sub C, and it's going to be equal to C sub X, which is X sub H. And then also you can find T sub C equal to F sub H, and then divided by cosine theta C. Okay, you can find this easily. And at this point also, if you have this angle at the theta A, let's see, this is going to be theta A, and you may project the T sub A here, okay, into the horizontal axis, and you can see that this is going to be T sub A cosine theta sub A, and it's going to be A sub X, which is going to be F sub H. And again, what you get is T sub A is going to be F sub H divided by cos theta A. Okay, that is a kind of equation that you can use. How the B? The B is unclear, so you may cut this by half. When you cut that by half, you may get the portion of the girder here, and also has the cable shape like this. Okay, and this cable is subjected to the no force of what? Of 850 kilonewton per meter, and the length of this, if you cut it here, this is going to be B, this is going to be C, and the length here is 41.42, so this is going to be 41.42 meter. Okay, and under this distributed force, some force must be developed. The force in the cable always in tension. Okay, and since the B is the lowest point, so the slope here is 0. Slope at B equal to 0, because it's the lowest point. And what we have is the coordinate here is like this, and you have this one as the T sub B. You have this one as T sub C, and UT sub C also have the component here and the component here. This is going to be C sub X. This is going to be C sub Y. This is going to be F sub H. And by doing this, okay, from free body diagram of the segment BC of the cable system, if you consider this, you have the no force, and this one we already have it for 36,456.9. Okay, and then what should we have if you do the summation of x sub x equal to 0 and put this one in positive? You will get this as T sub B equal to F sub H. It's going to be 36,456.9 kilonewton. Okay, and I should make a note again. The F sub H is horizontal force. The cable always have the horizontal force equal no matter the position of the cable is. That is have in the lecture. Okay, and then also if you do the summation of F sub Y equal to 0, you put this one up. Okay, and then you will get C sub Y equal to the C sub Y up equal to the downward is going to be 850 kilonewton per meter times 41.42 meter, and then you get the C sub X of 35,207.6 kilonewton. And as you may see, the T sub C can determine from the component of C sub X and C sub Y the force T sub C. The T sub C is gonna be what? It's gonna be square root of C sub X square plus C sub Y square. If you put this, it's going to be square root of 36,456.9 square plus 35,207.6 square, and then if you put into your calculator, you may get T sub C of 50,681 kilonewton. Okay, that means we may put the T sub C here. Okay, that is going to be 50,681 kilonewton, and also this one we have for 36,456.9 kilonewton. Okay, that is one way to determine the force T sub C. And if we go back to this relationship, we can check this one is correct or not. Okay, and this one gonna be zeta sub c. We also use this equation. From this we have the horizontal force already is 36,456.9, but we don't know zeta sub c yet. Okay, another way to find t sub c, we use this equation. So we start by find zeta sub c. Okay, from what? From zeta sub c, we come to this relationship tan zeta equal to 0.0233152x. Okay, we can find zeta sub c. Okay, what we have? We will have zeta sub c equal to tan power minus 1 of 0.0233152, and then what is going to be the x at c? X is going to be what? We move here. X is going to be 41.42. So this is going to be 41.42, and then you may get zeta sub c of 44 degree. Okay, and then t sub c equal to 36,456.9 divided by cosine 44 degree, and then you get the same answer, t sub c of 50,681 kilo Newton as before. Okay, they are equal, so it's proved. You may use the equation from the cable equation. You can get t sub c here, or you may use the free body diagram and equation of equilibrium. You got the same thing. So proof. Okay, and the last one, we gonna find the, oh, not the last one, but before the last one, we got the t sub a. So next, we find t sub a. And then again, we have the equation of t sub a before. Here is going to be t sub a, and is equal to f sub h, and then divided by cosine zeta a. And again, from the previous equation, zeta a equal to tan minus 1 of 0.0233152, and what is going to be the x for this is going to be the 58.58. So this is going to be here. It's going to be x at a. Okay, and then you will get zeta sub a of 53.79 degree. And when you put everything together, you get this one of what? Of 36,456.9 and divided by cosine 53.79 degree. You may get the force of T sub A. That is going to be 61,713.3 kilonewton. Okay, this is going to be our T sub A, and you may put the obtained T sub A is going to be 61,713.3 713.3, and you can see that this TA is what is the T max. This is the T max. Okay, and this T max occur at what? The angle theta sub A is 53.79 degree, and angle theta sub C, we have it here of what? Of 44. Okay, that is going to be 44 degree, and you may can see that the maximum tensile force occur at theta max. Okay, occur at the point of theta max. That's occur here, and you also can check. You can also check the T sub A cosine. The T sub A cosine. You may put T sub A cosine theta sub A equal to, you can prove F sub H as before. That is the equation we use here. Okay, and next we're going to determine the radius of the cable. Since we have the T max, we can determine the radius cable by using T max, which is equal to T sub A. And from this, we have any cable, even though we have this, is subjected to T sub A, and it's going to have the stress in sizes, and sigma max. Okay, sigma max is going to be equal to T max divided by the area required, the area that we are looking for. And usually the sigma max is to be sigma allowed. It's going to be as maximum it is. And then from this equation, you make like the A required equal to, you take this up here and you take this one down here. So it's going to be T max. And then divided by sigma allowed. And if you prefer, you may find A required equal to, this one is 61,713.3 kilonewton, and divided by we have what? We have 100 megapascal. That is going to be 110 power 6 Newton per square meter. So it's going to be 110 power 3 kilonewton per square meter. So this is going to be 110 power 3 kilonewton per square meter. And then you will get this to be 0.61713 square meter. And if you like to put it in millimeter, how we should do? You know that 1,000 millimeter is 1 meter. So 1 meter square is 1,000 times 1,000 millimeter square. So it's 1 million. So this one gonna be 617 133 square millimeter. And if you set this one to be what, pi r square, and then you put them together, you can determine the r of this to be 443 millimeter. That is going to be 443 millimeter. That's pretty big. That's nearly half meter diameter cable. And then we have this for 443 millimeter. Okay, we are at the end of this demonstration to solve the cable subjected to uniformly distributed load. What we have the cable equation, and we have this cable. When we have this cable, we take a look at this cable. We set the minimum point, the lowest point at the origin of the XY coordinate. And then we have the support pin, A pin and C pin. And then we set the location at the C to be X. And over here is 100 minus X. And then we are trying to find the cable equation. Before we find the cable equation, we need to solve for the position of B. To solve the position of B, we need to use the coordinate at A and C. And then by putting the coordinate of X and C into the cable equation, we got these two equations. And then it can right into this. And you can see these two equations have the same common coefficient here. So it can be equal. And then you can write the second order polynomial equation. And also you can solve the x. Okay, when you solve the x, you put the x back into one of these equations, but this is easier. And then you solve for the horizontal force. And you also need to recall from the lecture that the cable always have the same horizontal force on every point of cable. So that means this C sub x and A sub x also to be equal of F sub h. Okay, and then you can put the horizontal force into the cable equation and the uniformly distributed load, and then you get this as the equation, cable equation. And also you can determine the slope of every point of the cable. Okay, since the cable equation define the shape of the cable, so this one define the slope of the cable, or if you like, you can determine the angle of the cable. And then we are looking for the tension at A, B, C. And before that, we just cut the cable by a half. And then we can determine the free body diagram here. From this free body diagram, you can see the T sub B is equal to X sub H. As I mentioned before, that horizontal force at any point of cable is always constant and equal. And then you also can determine the C sub Y. Since you have C sub X and C sub Y, you can find the T sub C. And another way to find T sub C is going here. If you know the theta here, the T sub C cosine theta, T sub C cosine theta gonna be the F sub H. And then T sub C can find from this equation if we know theta sub C. And then we come back to this equation. Okay, we can find any theta if we know the x. That means while following this equation, we put the x. This is the x at C. We got the theta sub C of this. We put this, we get the same T sub C. Okay, and finally we find the last force in the cable is T sub A. T sub A also can find this equation, and zeta sub A also can determine easily by putting the x at A into the slope equation, and then you put it, you get the maximum. This is the maximum. Okay, and maximum occur at the maximum zeta. This is also zeta max. And then you got all the answer for the T sub A, T sub B, and T sub C. And finally, you can use the mechanics of material to determine the diameter roughly, preliminarily, the size of the cable like this. Okay, that is the end of this example to demonstrate you to solve for the cable subjected to uniformly distributed load. This is the clips show how to solve the problem of arch. This clip we are going to consider the circular arch, and this circular arch has subjected to the uniformly distributed load of 2 kilonewton. Okay, transfer from the girder at the top to the arch, and we're going to consider this arch as the arch system. So we won't transfer the uniform load to be the point load acting on the arch. This time we just consider the whole arch. Okay, and since this is the circular arch, it has the radius of 8.9 meter. So what it have, this arch going to has some kind of the origin of the arch somewhere here. Okay, if you have this 8 meter length and you measure this one for 3 centimeter, so if you have it's for what 8 meter, and then you measure 4 centimeter, and then you have 8.9 meter, it's going to be 3 times 8.9 divided by 8. That is going to be about 3.34 centimeter. If you like to do so, and you can show this, it's going to be like this. Okay, this is going to be the center of your arch, and this is going to be show you the portion of the circle to be part of our arch, and this is going to be 8.9 meter, and this is also 8.9 meter. And then it has the reference axis as support A. What it means is it's going to have the A at the origin, and this is going to be 0, 0, and then we have this one for X and this one for Y. Okay, and they ask us to determine the support, okay, at A, and the hinge at B, and they also ask us to determine the maximum compressive force, this will be here, and also the internal bending moment at point D. Okay, and put it here, and they said the point D has the coordinate 3 meter in the X and 2.363 meter to the Y. Okay, now if we consider the arch, and also arch has what? The pin support. So when arch has a pin support, arch going to have this one for A sub Y and this one for A sub X. I should note that all the forces at the horizontal of the arch gonna be in the point out direction like this. Because of what? Because if you imagine, if you push the arch down like this, okay, the support at the part of the arch at the A gonna trying to move like this. So the reaction supposed to resist it. The same thing, when you push it down, this guy gonna move like this. So the reaction of the arch always point in like this. Okay, that's for your note. And also we have this one for the c sub x and this one for the c sub y. And you may see the free body diagram of the arch system. The system has 4 unknown. Okay, and larger than 3 equation of larger than 3 equation of equilibrium. Okay, that's we must separate the arch system into 2 segments. Okay, and now we are going to separate this arch into 2 segments, and then we draw the free body diagram, and we will try to find the reaction that we have. And as you may know, the B is the crown and is the hinge, so this is going to have 2 more additional unknown, and when we cut it to be the AB and BC, so the problem is going to be easy. We're going to have 6 unknown and 2 times 3 equation. Okay, let's try to copy the part of this first. This is going to be 3 meters. This is going to be about 2 meters. Let me have this is for 3. And then this one is for 2. And then you can draw the circular. Okay, and then you get this portion of the arch of A, B, and also this way you may put this 1, 2, and 3, and this one you may put this for 1, 2, and then you may get the segment BC of the arch like this. Okay, and then there is the top beam. Just put the top beam onto this. Oops. Okay, it's going to be very rigid beam, and also we have the column. Okay, that is our arch, and on this side also. Okay, that is going to be B and C, and then we copy our reaction. That is going to be A sub Y, and that is going to be A sub X, and this is going to be C sub Y and C sub X, and on the top we have the distributed force acting upon it. It's going to be 2 kilonewton per meter, and this is also 1, 2, 3, and 4, and this is going to be 2 kilonewton per meter. And next we just put some length into this, and you may see this is from here to here is 8, from here to here is 8, so this is 8 meter, and this also 8 meter. And the crown going to have the distance from the horizon for 5 meters, so this is 5 meter and this is 5 meter. And at the B, we are going to have this one for b sub x going to be in the opposite direction, and also the b sub y, and also in the opposite direction like this. Okay, now we have the free body diagram of the segments of the beam, and we are ready to solve it with the 6 degree of, so see, or 6 unknown. So which way is the best way to find these 6 unknown? If you may consider, and as you may know from the lecture, the best way is trying to take the moment A to write an equation, okay, having b sub x and b sub y are the unknown. And then also we take another moment here to eliminate the unknown c sub x and c sub y, we get another equation. So by solving these two equations, we can get b sub x and b sub y. And after we can get b sub x and b sub y, we will have the a sub x and a sub y, and also c sub x and c sub y. Okay, consider free body diagram of this segment A, B. Okay, and we start with the summation of the moment about A equal to 0. So take moment here, and we have just do the counterclockwise rotation as the positive. And you can see the b sub x. B sub x have the line of action along here, and the line of action is 5 meter. Okay, this is 5 meter. So it's going to rotate what? In this direction, counterclockwise, right? So we have plus 5 b sub x. And also our b sub y gonna move like this, and the b sub y gonna have moment arm of this, and it's going to move like this. So it's going to be plus 8 b sub y. And our direction going to be here. It's going to be 2 times 8, that is 16 kilonewton, and it's going to be rotate clockwise. So it's going to be equal to, let's see, equal to 16 times half of this is going to be 16 times 4. That is going to be our first equation. And also we consider free body diagram of segment. This time is BC. Okay, and then we take the moment here, summation moment of C equal to 0, and that we have this counterclockwise is the positive. And see the b sub x now have the line of action here, and it's going to clockwise rotation, so it's minus b sub x, and then it's gonna time this, which is 5. Okay, and the b sub y gonna rotate down here and in the opposite direction of b sub x, so it's gonna be plus, and b sub y again, b sub y direction here is gonna time 8. And then we have this resultant force. Again, it's going to be 2 times 8 is 16 kilonewton, and it's going to rotate in this direction. Okay, it's gonna plus 16 times 4 and equal to 0. So by doing this, if you take the sign here, and you may rearrange this one to be 5bx minus 8 by, and then minus 16 times 4 equal to 16 times 4. Okay, you have another equation. This is going to be the first, this is going to be the second. And then you can use this calculator or hand calculation to obtain the b sub x, okay, and b sub y. And then what you get is the b sub x is going to be 12.8 kilonewton, and the b sub y gonna be 0 kilonewton. So we have this one is equal to 0, but the b sub x is gonna be 12.8 kilonewton. And then we go further, okay, by what? By summation of f sub x equal to 0, and then we determine the a sub x plus. So we have the a sub x, and then we have this one is the b sub x. A sub x equal to 12.8 kilonewton. And the last one, summation of f sub y equal to 0. You may put the a sub y is up, so up, okay. And what we have is the a sub y equal to 1. A sub y, this is 0, so a sub y equal to 16.0 kilonewton. Okay, and if you like, you also can do this for the BC portion, summation of x sub x equal to 0, and you're going to find c sub x. Put this into positive. So your c sub x, your c sub x gonna be 12.8 kilonewton. And you may see all the c sub x, all the force in the x direction, they are equal. This is special because our arch has no horizontal force. That's why all the force in the x direction of this problem are equal. Okay, and then you do the summation of f sub y equal to 0. That means you're going to take the c sub y plus, okay. You have the c sub y of what? C sub y is up, c sub y, and only the 16 here, c sub y equal to 16 kilonewton. Okay, this is equal. Y is equal. This is equal due to symmetry of the arch. So the c sub x is equal to c sub y. Okay. Okay, what we have now is the a sub x, okay, of what? A sub x of 12.8. This is going to be 12.8 kilonewton in this direction. And the a sub y is 16.0 kilonewton upward. And b sub x over here is going to be 12.8. Okay, it can be both direction. And b sub y is 0. Okay, that is the first part that we get, and we may make some note on this, right? The a sub x is 12.8. So if you put this on scale, this one gonna be 12.8 divided by 2, about 6.4. If you do this for 6.4. And then this one for 16, that's divided by 2, that's about 8 millimeter. So you got this. And if you do some kind of projection, okay, you may get the resultant of A. Let's us call this one as the R sub A. And also this one, if you like, you may do the same thing. The 16 divided by 2 is 8 millimeter. Okay, and that is going to be what? 6.4 divided by 2, 6.4. And again, you may get this. And this is going to be the R sub C. Okay, and the resultant of this is going to be equal because what? Because they are in symmetry. Okay, and then what we have is the maximum. The maximum compressive force okay, force is occurred at the support A and B. Okay, from the figure we can see that A and B, and it's going to be equal to the square root of this is going to be 12.8 square plus 16 square, and if you put it in your calculator, you will get this for 20.49 kilonewton. So now you get the what? You get the maximum force, which is 20.49. Okay, and then you put this into this one is going to be 20.49, and it's occur at A and C. Okay, A and C, support A and C. So this one is going to be 20.49 kilonewton at the support, and we can find the angle. Okay, if this one say theta A, and if this one also theta C. Okay, we can determine the angle. The angle theta A is, if you do this, you can find the angle theta A, right? Is the angle theta A. By this one, we're going to have the ratio of what? This one going to be 16. This one going to be 12.8. So we have the tan theta A equal to the vertical 16 divided by 12.8. So the theta is arc inverse tan with the 16 divided 12.8, and you will get the angle theta C, if you like, to be what? What did you get? I cannot find it here. Okay, we get it for 51.3. It's going to be 51.3 degree, and it's going to be equal to this one, theta C is going to be equal to theta C. This is important for what? This is important for you to know because you're going to build the foundation. Okay, to build the foundation in that angle to support the force from the arch. So this is also important angle at the theta A and theta C, because you're going to design the foundation for that. And then we have one thing left, the moment at M sub D. If you like to determine the moment of M sub D, you got to you got to draw the free body diagram of this portion. Okay, next, just put here, find the M sub D, and then we may project this portion of the arch, okay, with its portion here, and we can find the internal forces and moment at D. By doing that, let's just put this portion, and then this is the A, this is the D, okay, and what we have is, let me put this one on the top, that is going to be the free body of this portion of the arch, and then we have this one for 16 kilonewton, and this one for 12.8 kilonewton, and also we have 2 kilonewton per meter. Okay, when you cut it like this, the here is going to be the point D. The point D, you also project here. Okay, the point D is going to be, this is going to be in parallel to this. Parallel yet? Okay, now it's parallel. Okay, you got this. Okay, you can see that this section gonna have the normal force, okay, acting perpendicular to it. That is gonna be N sub D, and also it's gonna have the shear V sub D here. And what in the question is, they ask us to determine the M sub D. Okay, and by doing this, we can determine the M sub D easily by taking the moment at this point. Okay, so we're going to eliminate the V sub D and N sub D by taking moment at D. Okay, before we can do that, take this one of 3 meters, and this one of 2.363 meter, 2.363 meter. Okay, and then just the summation of moment at what? At D equal to 0. And since it's moved like this, just put this is the positive. So we have the plus M sub D. That's the plus M sub D. And then what else do we have? The force here, 12.8 kilonewton, going to have the moment arms here, and it's going to rotate by this direction, plus 12.8, and time this moment arm of 2.363, okay, meter. And then you also have what? Have this. This is going to be 2 times 3, that is 6 kilonewton. And the distance from here to here is going to be 1.5. And it's going to rotate the same direction. So plus 6, and it's going to time 1.5. Okay. And then we have this 16 kilonewton. And it's going to be in the opposite direction. So minus, this is going to be 3, 16 times 3, and then this is going to be 0. And you put this one, you get M sub D equal to 8.75 kilonewton meter. So as you may know, only the parabolic arch has 0 m sub d and 0 v sub d and has only n sub d. But the other arcs, they have m sub d, they have the moment, and we can show you that this circular arch also has the v sub d and n sub d. So now we put this one 8.75 and have the direction here. Okay, let's just trying to show you about the v sub d and n sub d. If you extend this line further, and then you may use this one to estimate the angle of this. Okay, and you may see this is going to be about let's say it's going to be about 50 kilonewton, 50 degree. Okay, just put this one, okay, to be the 50 degree. And then if you project this down to cut this is going to be 90 degree. And you may see that this angle is going to be 40 degree. Okay. And also, if you may see, this is 50, so this is going to be 50, and that's why this is going to be 40 degree. Okay, if you get the equation like this, next you can find the force. Okay, this is going to be n sub d cosine 40 degree. Okay, and also if you project v sub d in this direction, you will get this as the v sub d. V sub d what? V sub d sine 40 degree. Okay, and if you do the summation of x sub x equal to 0, and if you like, you may put this as the positive, so you get what? Minus n sub d and cosine 40 degree, right? And you're going to get plus v sub d sine 40 degree, and this is going to be 12.8. Okay, you may put this plus 12.8, and then it's going to be 0. Okay, that is the first, let's say it's the third equation. And then you may do the same as the summation of f sub y equal to 0. And this time, if you project this one, you may get this one, the downward. This one gonna be n sub d sine 40 degree. And also if you project this, you may get this one as v sub d cosine 40 degree. Okay, if you put this one is the positive, so you have n sub d sine 40 degree is n sub d sine 40 degree, and then you're gonna plus v sub d cosine 40 degree and plus 6 kilonewton and minus 16 kilonewton, and then you get this one equal to 0. So you get the equation number 4. Okay, showing the simultaneous equation. Okay, we have, you got to stop the clips and then trying to solve for what? For n sub d is going to be equal to what? Kilonewton. and also V sub D is going to be equal to how many kilonewton? Okay, and I will give you the solution. The N sub D gonna be 16.2 T, and V sub D gonna be minus. That means it's going to opposite this direction, 0.57. Okay, that's all we have for this example. We do the example of what? Of the circular, okay, of the circular arch, and our circular arch has the pin support. Okay, so if we just consider the whole arch, we have 4 unknown, we cannot solve. That's why we got to separate the arch. Since the arch have the hinge at B, it's a kind of 3 hinges arch. Okay, by doing this, we just take moment for the free body diagram. We take moment at A, we got this equation, and we take moment at C, we got this equation. By solving the simultaneous equation, we got the B sub x and B sub y. And after you get the B sub x and B sub y, you can determine the A sub x and A sub y. And then we got all the result. Okay, A sub x, A sub y, B sub x, B sub y. And if you like to check for the C sub x and C sub y, you can do the same thing, and you found the structure is symmetry. That you have C sub x equal to B sub x equal to A sub x, and if also C sub y equal to A sub y, and then you get the maximum compressive force at both, okay, at both support. And one of more important thing, you just determine the maximum compressive force easily by putting into this equation as we have. This is the resultant force. And I also to mention the angle between the resultant force and the horizontal force are also important, because we're going to design the foundation. The support is maximum compressive force properly. Okay, and then we move to consider the only small portion of the arch, that is going to be the AD, and then we also find the M sub D here. Let's show you the circular arch have some moments internal. Okay, and not only the bending moment inside the segment of the arch, we can also determine the shear force and the normal force. That is the end of this example. This script is the demonstration of the learning objective 1 to draw the influence line diagram of the reaction, of the shear force, and of the bending moment. Okay, that is the learning objective 1. And then we will put the given uniformly distributed dead load. If you have it, it's going to be dl, the dead load, and uniformly distributed of 150 kilonewton per meter. And the concentrated live load, that is going to be LLF of 50 kilonewton. We will put these two loading into the influence line diagram to determine the maximum reaction and to determine the maximum moment. That is going to be the learning objective 2. Okay, so let us practice first by draw the influence line diagram. We will use the Mueller-Based law principle to draw the influence line diagram. First, they ask us to draw the influence line diagram of the support D. So you may recall from the Musler-Best law, if we like to draw the influence line of reaction at C, so we got to eliminate the resistance of C sub y out. Okay, just eliminate it. And then you put the C sub y into that position to move this point into 1.0 unit. Okay, so before you can move, you got to fix this one with the fixed support. This is fixed support. Okay, and then we have hinge here, and this portion link, okay, in the form what we so call the rigid beam. When this all are rigid beam, portion of the beams are rigid beam, so the change in the shape of the beam will be in linear manner. Okay, and then since this one is fixed, okay, and this one is the hinge, and then you put the C sub y in that direction. The hinge here gonna be the rotating point, and then the shape of the beam will move like this. Okay, and if you scale it by a half centimeter to be 1.0 unit, and then the shape of the graph will be like this. And what is the coordinate of this? As you may know, if this is y, we will have y divided by 2, 4, 6, 8. Y divided by 8 equal to what? Equal to 1 divided by 2, 4. 1 divided by 4. So you got y equal to 8 over 4. That is going to be 2. That is the Muller-Best law principle. If you like to draw the influence line of reaction, you eliminate the resistance or you eliminate the support, okay, of that reaction, and then you put the reaction to move the beam segment for 1 unit. The obtained shape is the influence line diagram of the reaction. Next, let us consider the influence line diagram of shear force at D. Okay, before we can do that, at D is here. The support here is fixed. Just put it fixed. And this is hinge, and this is roller. The support are the same. And if you like to draw the influence line diagram of shear force SD, the Muller-Best law said we going to eliminate the shear force at point D. By eliminate the shear force is the relative displacement. We put the roller guide into that point D. Okay, and when you put the roller guide, then you may again, like before, you put the V sub D, okay, V sub D to move the beam, and the shape of the beam will be the influence line of the shear force SD. And also, we should to recall that if we cut a section of a beam, okay, this is very long beam, for example, you get what? You get the moment gonna be like this to be positive M. And also by doing that, the shear force on the left is going to be downward, on the right is going to be upward. So this is going to be the sign convention of positive V and positive N. And then what happened? This portion is fixed, okay, to the wall. And then if you put the V sub D down here, what happened? There is no movement of this portion because it's very steep. Okay, it's very steep. And then if this one won't move, the thing is this one gonna move for 1.0 unit. Okay, that's it. Obligation to draw the shear force influence line of the shear force. And also what happened is the portion of this must in parallel with this rigid beam. Okay, and that will make this hinge move also. And then the last one, this one, when hinge move, this is the rigid beam have the rotating point at C. So this one gonna move like this. Okay, and then you get the rotating BECF to be the shape like this. And what happened is, this is gonna be 1.0 and this is gonna be Y. Okay, and you're gonna have Y over what? 2, 4. Yes, Y over 4, right? Y over 4 equal to 1 divided by 2, 4. 1 divided by 4. So you will have Y equal to 4 over 4 equal to 1. Okay, and since this is negative, okay, so this one is going to be minus 1.0. That is the influence line for the shear force at D. Okay, next, they still ask us to draw another influence line of shear force, but this time they said at E. Okay, as E. Where is E? E is here. Okay, before we interested in that, we put this one as a fixed support as before, and this is hinge. This is gonna be the roller. And to draw the influence line diagram at point E, we do what? We eliminate the resistance of shear force at E. By eliminate that the shear force at that point, we put the roller guide into it. Okay, and then we like to move this one. We put the what? Plus V sub D to act. Okay, along the guideline. Okay, roller guide. And again, the same thing happened. This portion won't move because it fixed support won't rotate, so it won't move. Okay, and by the rotating here, this one have the hinge and this one move downward. Okay, and it's going to move downward forward. Is going to move downward by minus A over L. Okay, that's A over L, and it's going to move upward plus B over L. And what is A? You go back to consider this. Okay, and your interesting span is here. So the L will be 4 meters, and this one gonna be the A. This one gonna be the B. So we get this one minus of what? 2 divided by 4. Or you have minus 0.5. Same thing is over there. It's going to be plus 0.5 movement. Okay, and then you have this is half. When this is half, so this is going to be 2.5 millimeter. And then you get this portion to rotate like this. And this portion also 2.5. And then you get this rotation. And the sum of this gonna be what? The sum of this gonna be 1.0. Okay. And one more thing, they are gonna be in parallel. Okay. And also, if this is Y, you will have this is for Y 2, 4. Y divided by 4 equal to this is 0.5, right? It's going to be 0.5 divided by 2. So you get Y equal to 0.5 times 4 and divided by 2. So it's going to be 2 divided by 2 is 1. However, it's in negative. So this one is minus 1.0. Okay, this is another influence line diagram of shear force at E. Okay, and next we're going to draw the influence line diagram of the bending at point D. We go back to the point D. Point D is here. What we do is changing, eliminating the resistance to moment at D. So we're gonna put what? We're gonna put the hinge into at point D. Okay, and this hinge going to be the same. The support here going to be the same. Okay, this beam is rigid connect will be the same, and the one more thing, the roller SC is here. Just put it here, and then what should you do? Just put the moment M sub D. This is D positive M sub D positive M sub D to X here, and then what happened is this is stiff beam, and then if you like to rotate it, the fixed support won't allow the rotation. See, so this one will not allow, will not move at all. So what happened is the portion here must move, and it must move for 1.0 radian. Okay, and then since this is 2, okay, and this is rotated by 1.0 radian, so this one gonna move to here, and this is gonna be -2, and then you get the shape of this to be like this. And again, this is rotating point. When you move this one like this one gonna rotate in this shape, right? Okay, we have what? We have this connecting point. All the beam segment must rotate in the straight line because they are rigid beam. Okay, and then if this one is -2 divided by 4, this one gonna be y divided by 4. So we can calculate this to be plus 2.0. Okay, next, the last one, we gonna consider what the point E. Now we going to draw the influence line of E. E is where? E is here, as we know. Okay, as we know, E is here. So we must eliminate the resistance to bending moment at E. That means again we put this hinge into E, and this hinge still the same. The support here fixed, and we also have the roller here. And what happened is we got to put the M sub E, the positive M sub E as before, as M sub D here, positive. This one and this one is going to be positive M sub E. What happened is this portion again won't move, but this time we have what? We have the hinge here, and now we trying to open it up. Okay, so when you open it up like this, you may see the link between the tips of the pins, right? So this one gonna move to somewhere here with what? With the coordinate of A, B divided by L. It's going to be 2 times 2 divided by 4, which is 1, right? Which one? So this one gonna move by our scale to here. Okay, only this, and this is going to be 1.0 plus, and this one gonna move up to link this, right? And this one gonna move downward like this, and we have, oh sorry, this is more than we need. Okay, y, and then y divided by 2 plus 2, 4 equal to this one is 1 divided by 2. So we have y equal to 4 divided by 2. And then it's gonna be 2.0. And since it's in lower area, so it's gonna be minus 2.0. This is the first objective of our learning, to draw the influence line diagram, okay, of the given beam. And next, the learning objective 2, we will find the loading pattern. Again, please recall that we have what? We have the distributed, uniformly distributed dead load. The dead load have some characteristic. One is gonna be distributed along the whole length of the beam, because most of the dead load is the cell weight of the beam. You cannot eliminate it. It's going to be total there. And another one, we have the concentrated life load. Okay, that is going to be a kind of point load. When you point it, you're going to find the maximum coordinate for the most influence area, or it's a larger area. Okay, let's ask first, they ask us to find the maximum reaction at support C. That means we're going to use this influence line as support C. And then they ask us to the maximum at moment at E. So we're going to use the influence line of the bending moment SE, right? Okay, let's remove this one a little bit like this. And then here we come. Okay, we have the beam there. Here, influence line of R sub C is here. And if you like to find the loading pattern, we can see that the area of the influence line of C sub Y, all of them are plus. Okay, so the concentrated life load gonna be at largest coordinate. So we will put this concentrated life load of 50 kilonewton at this point. So for that reason, you will get the concentrated life load here. Okay, 50 kilonewton. And for the dead load, it's going to be along the length of the beam. Okay, unlike the concentrated life load, if we have the concentrated life load for this problem also, we will put the concentrated life load in this area. Okay, or you may put it like this on the top of the dead load. Okay, but this one we won't have, just take it out. So this loading pattern gonna produce the maximum C sub Y. And then recall back the point load gonna time what? Gonna time the coordinate. Okay, the coordinate here is 2, so it's gonna time 2.0. Okay, and the uniformly distributed load, sorry, is 150 kilonewton meter. Gonna time what? Gonna time the whole area of this influence line diagram. So it's gonna plus 150 kilonewton per meter. And the whole area is what? It's gonna be 1/2 of what? Of the base. 2468 times 8. And then time over here is 2. Okay, so what we have here is, over here is gonna be 100 kilonewton. This is 100 kilonewton, 50 times 2. And it's going to plus, this is cut, 8 times 150 is going to be 1,200 kilonewton. So finally we get the C sub y by this loading pattern to be the maximum as 1,300 kilonewton. Okay, that is understandable, right? And the second one, now we come to find the loading pattern for the maximum moment at E. Let me zoom this because the moment E is here. So what we have is there is two areas here. When we determine the maximum influence, we will consider the area under the influence line diagram. If the area is larger, is going to produce the larger influence. It's going to be the governing portion. Okay. Anyway, the distributed dead load won't make anything. Just put the 120 kilonewton per 150 kilonewton per meter as before along the whole length. Okay, and then we can consider the influence of this. This is going to be 1/2 of what? Of 4 meter, and then time this one for 1. So this one gonna be 2. Okay, the area is 2. This one is 1/2 time 2 plus 2 time 4 and time 2. So this one gonna be 4. So the negative area, the yellow area, gonna produce maximum influence for M sub E. Okay, so what we should do is we're going to put this 50 kilonewton, okay, at the largest coordinate of this yellow area. So if that happen, you got the same loading pattern, okay, and the M sub E gonna be 50 kilonewton, and time what? Time this one time minus 2.0 is negative. Okay, and some of the area here gonna produce the negative also, right? So it's gonna be plus 150 kilonewton per meter, and time this area, and this area is 4 negative, so time minus 4, and the other portion here gonna produce positive effects. So you pass this one for 150 kilonewton meter, and then you get what? You get this one for minus, so plus 2. So we will have this one for minus 100. This one is minus 100. This one could be minus 600. Minus 600. And this one gonna be plus 300. Okay, and finally you get the M sub E of minus 400 kilonewton meter. See, that is quite understandable, right? You guys will do it with some listening. Okay, it's not a guess. You must do it with some thing that's explainable. And then you got this for 1,300 kilonewton, and the moment at E of minus 400 kilonewton meter. Okay, this is the end of this example. Today I'm going to demonstrate you how to determine the absolute maximum shear force and the absolute maximum bending moment that's going to occur on the 30 meter long simply supported girder, and is also subjected to the moving load. The moving load on this problem is kind of big one. It has 4 of the point load acting on the wheel of this vehicle, and it's going to pass to the 30-meter girder of the bridge. And when we start to find the maximum shear force, it's going to be the absolute maximum shear force. You have studied about determine the maximum shear force before, but for the absolute maximum shear force, everybody know that this is going to occur at what? At the support, right? Because well, most of the force, shear force, for example, for a simple beam like this, subjected to the force at the middle of the beam, and you may see under this force P, we will have this reaction of P over 2. And if you draw the shear diagram of this beam, you may see that the maximum shear force, okay, for this one occur at the support, okay. And if you change this one to subjected to a uniformly distributed load, okay, for W, you may see that this one gonna have what? Gonna have WL over 2, and this one also W span over 2, and the maximum shear force will occur at the support again. So most of the time maximum shear force occur at the support, okay. And for this kind of beam, let me move the load to this size. If you guys compute, we will find this reaction will larger than this reaction, and then the shear force gonna be large on this side and smaller on this side. Anyway, these 3 cases show you that the maximum shear force is occur, okay, is occur at the support of the beams, okay. Mostly is occur at the support of the beam, and the absolute maximum also is may occur at the support A, and is also may occur at the support B for the absolute maximum shear force. And most of the time, the absolute maximum shear force on the support will be equal, okay. So if you like to determine this, you got to move the vehicle passing the bridge, and this time let me consider to find the absolute maximum shear force at the support B, okay. And by doing this, let me try to draw the girder first, and what we have is 30-meter girder. And if you measure this, you may see, okay, you may take this one for 10 centimeter if you like, okay. And you will put the load into this portion, or if you like, you may put on the A, it's no matter. It's going to get the same result, but I prefer to put this example to the support B, okay. The step of determining the absolute maximum shear force, okay, this is the A. We're going to determine the V absolute max, and we know that the maximum shear force occur at the support of the beam, and we will draw the influence line diagram of this time. We interested at B. Okay, let me is at B, and you make try to work for the A. Okay, let's see. In terms of B sub y, and by doing this, let me take this for 10 centimeter, and let me put this one to draw the inference line of b sub y. So the a going to be the same, and since b is the pin, okay, let me release or eliminate resistance to the b sub y. However, the resistance to the b sub x still there, and then we push this beam up by the reaction b sub y for 1 unit. Okay, it's going to be up for 1 unit, and then what we have is the shape of the girder, which is the influence line diagram of b sub y. And you may see we have the point load. When we determine the reaction of the shear at b, we will multiply the magnitude of this point load with the coordinate of the beam. So the next step, we will put the loading, the moving load, the loading pattern to the girder. So what the loading pattern that we can move, since the beam have the tuck like this, and since the influence line of b sub y opposite, so the maximum should occur when the load all apply to the beam. Okay, let me start. First, we just say this car going to collide. Okay, and then we put another way the vehicle going to collide. Okay, and the other way the vehicle go to Bangkok. And by doing that, we will have 2 cases. Okay, let me put the first one like this, and we put what? We put the 45 kilonewton here. When you put the 45 kilonewton here, this is gonna be 45, and the car is what? 4 meter, 3 meter, 4 meter. What we have now that I said is 10 centimeter for 30 meters. So the scale that we use, the scale is going to be 3 meter per 1 centimeter. So 4 meter gonna be like about 1.3 centimeter, 1, 2, and 3. Okay, that is going to be 160, and another 3 meter, that is going to be 1 centimeter, that is the 90, that is going to 90, and it's going to be 4 meter, that is about 13 centimeter. So the load gonna be, the first case is like this, is 160 kilonewton, and this is going to be 90 kilonewton, and this one also going to be 90 kilonewton. Okay, that's me consider the first case of this. And in the opposite direction, okay, this time the 45 kilonewton will be moved into this direction. Let me put this one to the beam again, and okay, this time this is the pin, and this is still the roller, and this time the 45 kilonewton is going to be on this direction. So we should start by putting the 90 here. Okay, so this time we put the 90 kilonewton here, and then it's going to be 1.34 meter. That is going to be like 1.3, but it's going to be the same as this. This is going to be 4 meter, and it's 90 kilonewton. It's the reverse of that. And then 3 meter, that is going to take for this. It's going to be alignment with the previous one. That is going to be 90. This is 160. This is 160 kilonewton. And the last one is going to be this one, and it's only 45 kilonewton. So this one move in the opposite direction of the first one. Okay, and there are some cases that we need to put, you know, 3 of the wheel loads onto the beam also to consider to be the author step. And let us check. Okay, whether the 3 load that put on the girder gonna produce the maximum shear force or not. Okay, just tie is 2 different cases, but 2 wheel loads won't for sure, but the 3 and the 4 maybe. Okay, and we have this time, let's take this 45 kilonewton out. Okay, let's take that 45 kilonewton out and put the 160 kilonewton here. Just put the 160 kilonewton here. So let me put this one here, 160 kilonewton, and then the 45 kilonewton gonna move out to this position. Okay, that is going to be 45 kilonewton, and then we have 3 meter. 3 meter that's going to be 90 kilonewton, and we have 4. Okay, that is going to be about this. Okay, we have this one for 90 kilonewton, and then this is 4 meter, and this is 3 meter. Let us check like this. This is going to be in the different location. Okay, this one going to be at the same point, and this one going to be at the same point. Okay, and another interesting thing, in case that are supposed to occur when this one. Okay, we move the 90 here, and the other gonna move in accordance with also. Okay, by doing this, we consider 4 cases of them. This one, the 90 gonna move. This 90 is going to be here. Just put this one as the 90 kilonewton, and this 4 meter just take away from here, and that is going to be 90 kilonewton. Let's move out into this way. Okay, and sorry, and this case, what we should have is what? Should have is what? This one move here, and this one is 4 meter. So you have 3 meter between this one and this one of 160. This is 3 meter, and this one is 160 kilonewton. Okay, and the last one is gonna move for 4 meter, so it's going to be 45 here. That is going to be 45 kilonewton here. So this one going to be like this. Okay. Okay. We have 4 cases, and then what we should do is next step. Compute the maximum shear force for each case. Okay, for each case we have total of 4 cases. So case 1 is here. Let me put it in the red. Case 1. In the case 1, what we have is the 45 gonna time 1. Okay, and 160 gonna time this. Okay, and then 90 gonna time this coordinate, and the 90 gonna time this coordinate. So let us compute the coordinate of this. I set this one to be the B, this is going to be y sub b, this is y sub a. Okay, y sub a is okay, is equal to 1. Y sub b, this is c, this is y sub c, this is d, this is y sub d, and this is e, this is y sub e. And by similar triangle, okay, by using similar triangle, we have what? We have 1 divided by the total length of the beam of 30 meters. So 1 divided by 30, and it's going to be equal to, this is going to be projection, this is going to be 3 meters. Okay, this is 3 meters, and it's going to be what? Y sub b divided by 27, y sub b divided by 27, and then the difference between this one and this one is 4 and 1, so it's only 1 meter here. So y sub c divided by, this is 4, y sub c divided by 30, and then minus 4 is going to be 26. Okay, and then between this and this is going to be 3 meters. Okay, that is going to be 3 meters. So this is 3, 1, 3. It's going to be 7. So the distance here between my finger and the tips of the pencil is going to be 23, right? That is going to be y sub d divided by 23. And the last one we have, this is 4 meters. So this one plus this one plus this one and plus this one gonna be 11 meters, right? So the last portion over here is going to be 30 minus 11 is going to be 19. So this is going to be y sub e divided by 19. Okay, by doing this, you can compute y sub b equal to 27 divided by 30. Okay, this is going to be 27 divided by 30. And the next one is going to be 26 times here, and it's going to be 26 divided by 30. And the also one is going to be this. This is going to be 23 divided by 30. And the last one going to be 19. It's going to be 19 divided by 30. Okay. Okay. So we are ready to compute the maximum shear force for each case. So the case 1 we have for the case 1. Let me compute. Let's say this is By, and you may know the By is equal to the maximum shear force at B. The maximum shear force at B. Let's say at B for each case. So this B sub y is going to be 45 times 1. 45 times 1. And 160 plus 160 times 26 over 30, right? 30. And plus this is 90 times this one, plus 90 times 23 over 30. And the last one plus 90 times 19 divided by 30. That is going to be the case 1. And then you put everything into your calculator and do it slowly. You may get this force to be 309.7. You may pause the clips, okay, and try to compute, put thing in your calculator. So the second one, we have case 2. Case 2. The case 2, this 2 is here. So the B sub y gonna equal to what? 90 times 1. So we got 90 times 1. And then we got another 90, but this time is 4 meters. So it's gonna time this one. it's going to be plus 90 times 26 over 30. And then we move another 3 meter. So this coordinate gonna time 160 plus 160 times 23 over 30. And this one is 45 and plus 45 times what? 19 divided by 30. And then you get for the second case of maximum shear force at B. Okay, stop the clips if you like and put the number into your calculator. You may get this one a little bit higher than the case one is 319.2. Okay, and then we have this one, the third case 3. We have case 3. And what we see the case 3, in the case 3, the 45 out of the influence line diagram of B sub y. So it's going to be 45 times 0. And then we have what? 160 times 1 plus 160 times 1. And this one is 3 meter. So the 90 gonna time 27 divided by 30 plus 90 times this one 27 over 30. Okay, and another 90 kilonewton, that is 7 meter. So it's time this plus 90 times 23 over 30. And then you get for the third case. Okay, and you put this one into kilonewton. And if you do it slowly, you may get this one 310.2. It's larger than the first case, but it's less than the second case. And then we have the last one for this case. Okay, we have what? We have case 4. This one. This one is going to be case 4. On our case 4, our B sub y gonna equal to this 90 times 0. 90 times 0. And this 90 gonna times 1. Okay, this is 90 plus another 90 times 1. And this is 3 meter. And 160 times this one plus 160 times 27 divided by 30, and plus the last one 45 plus 45, and this one is 7 meter, so it's going to be 23 over 30. And then you get this going to be 268.5. So the last one 268.5 is going to be the smallest one. Thus we have what? Thus therefore we have V absolute maximum equal to 319.2 kilonewton. That is the absolute maximum. That means it's a maximum of the maximum, right? So you got this for max is occur at B. And if you like, you may try to do the same thing at the support at A. Okay, I think you can do that, right? Okay, we finish the first part, and then the second part, let's say the B, we are going to determine what this time? We determine the M absolute max. And you may understand that for the simple beam, most of the time, the maximum moment occur near the midspan of the beam. For this one, the maximum going to be have the shape like this, and this one going to be a max. See, it's going to occur near the center of the beam. And also for this one, sure, you guys can draw this. Again, the maximum moment gonna occur near the center. Okay, but for this one, since the force just move anyway, the maximum going to be in this portion. So you can see that by considering the simple beam, the maximum moment most of the time occur at the area near center of the beam. We can maximum bending moment is usually occur in the area near the midspan of the girder. Okay, so by this concept, and if you may recall from the lecture, we will put this car in the center or the midspan of the beam. But before we can put that, we're gonna find first the resultant force, the F sub r of this series of moving loading, and we also need to determine the what's so called the location of that F sub r. Okay, and based upon that, let me consider this series of loading and trying to expand them a little bit more. So it's going to be 433, and that's it's going to be 1.3. Okay, and then 1, and then another 1.3. Okay, that's it's going to be 1.3 and 1, and that is 4 meter. Let's see, it's going to be 4 meter and 3 meter and also 4 meter, and then you get the force acting on this one of 45 kilonewton, and over here is 160. This is going to be 160 kilonewton, and the other gonna be 90 kilonewton, and this one gonna be 90 kilonewton. So the first step that we may have, we gonna find or compute F sub r. Okay, this is gonna be what? The F sub r is gonna be the summation of these forces of 90 plus 90, and then plus 160, and then plus 45. That is going to be put it into the calculator, that is going to be 385 kilonewton. That's going to be the first. Okay, and then the second one, we find the location of F sub r, phi x bar. So what is going to be, and I think it's going to be somewhere between here, because it's 180 here, it's going to be 205 here, so it's going to be very close a little bit to the 160 kilonewton. Okay, let me put this one into this position. It's going to be half, right? This is going to be this is 205, this is okay. Let's put this one about here. Okay, and it's going to be the F sub r. And by putting this, you're gonna set up the reference line, if you say this is going to be the reference line, you may determine the x bar, okay, by taking the moment about this reference line, okay, by using the concept of equivalent, by using the concept of equivalent moment, okay, and then what we have is going to be take the moment about this point f sub r times x bar, so we have 385 times x bar, okay, and this moment rotate in this clockwise direction, so it's gonna equal to this, going to produce for the equivalent moment, it's going to rotate at the same direction 160 times 3, it's going to rotate this way, so 160 times 3, and 45 going to rotate this times 7 plus 45 and then times 7, but we have this one going to rotate in opposite direction minus 90 and times 4, then this 90 produce no equivalent moment, but this 90 going to produce the minus 1, so we will get the x bar, this x bar going to be what, 1 point, put it into your calculator, pause the video, and it will be 1.1298, okay, so and then the concept of finding the absolute maximum moment, we going to put this loading to the area, okay, of the midspan of the beam. So first one, we gonna divide this x bar into two parts. Let me divide this one into two parts, and we will put this into the midspan of the beam. Let me put this one in, okay, let's say in this area. Actually, this one is not good. We may take this one out. Sorry for this. The design of the examination is not that compatible what I'm working here, okay. When you do this in your examination, try to work incompatible with that. I have the problem because I'm going to record all I'm writing. That's why I have the problem with this line. Okay, let me have this. We have what? We have the beam again. This beam is here. Okay, we put the beam here. This is 10 meter beam. 30 meter beams with 10 centimeter on this, and then we have this as the roller, and we have this as the pin, and the center of the beam is going to be 15 meter and 15 meters, so it's going to be 5 meter, and this is going to be okay. And if you do this, this is going to be half of the length, 15 meter and 15 meter. What we have now is we going to put this half of the x bar. What is going to be half of the x bar? If you divide x bar by half, the distance here and the distance here gonna be what? X bar divided by 2. So x bar divided by 2. is going to be equal to what we have 1.1298 divided by 2. It's going to be 0.56 and 49 meter, and they are going to be equal. Okay, so we put the green over here, right here. Put the green right here, and let me zoom this one more so it's going to be clearer for us to work on this. We put the green here. When you put the green here, what happened is you measure to the left, okay, for 0.5649, you get the 90 kilonewton. So this is when you do the scaling. Scaling what we have is 1 centimeter for 3 meters. So 3 meter is for 1 centimeter. So we have about 0.5649. It's going to be 0.5649 divided by 3. Okay, and time 1. That is about nearly 2 millimeter. So just put this one about nearly 2 millimeter. Okay, the 90 kilonewton gonna be here. This 90 kilonewton of the reference line, 90 kilonewton. And then you move another 4 meter. So that is about 13 millimeter. And then you get another 90 kilonewton. This is 4 meter. And then you move 3 more meter. Okay, you got 160 kilonewton. 160 kilonewton. And if you move 4 meter, that is about 13 millimeter. About, you put this one for the scaling, that is going to be 45 kilonewton, and then this 4 meter. Okay, and you also have the F sub R here. That is going to be 0.5649. So that is going to be by scaling of this, about this. This is going to be your F sub R, okay, of 385 kilonewton, and the distance of this is gonna be reflect back here and reflect back there. Okay, and now by the lecture, the absolute maximum moment will occur underneath the wheel load that's closest to the midspan of the beam. So for case one, we will find the M max here. Okay. Third. Loading pattern one. Okay, pattern one. And what we have, we will determine what the beam on just this portion, the maximum moment will occur. Okay, I will write later. Just me put this one first to make it. So we will consider this free body diagram, and to consider this portion of the beam, that means we going to determine the A sub y, and it's going to X here. Okay, and the maximum moment gonna occur here under the 90 kilonewton. So this one is 90 kilonewton, and this one also the 90 kilonewton. This is 4 meter, and the length of this is what? this is going to be 15 divided by this. So this one going to be 15 minus this is 0.5649, and you may have this one for 14.4351. This is 14.4351 meter. So this is going to be the length of our beam segment that we are going to use to determine the M1. This is going to produce the M1 and the shear also here. Okay, if you guys have this, we just zoom it a little bit out, and then we have the compute area here. The maximum moment will be occurred, okay, at the location under the wheel load that is closest to the mid span of the girder. That is going to be the principle for this one, and we did prove it from the previous example. Okay, so from the free body diagram of the girder A, B. Okay, we just take the moment about here, summation of the moment about, let's say, B equal to 0. So A sub y gonna rotate this way. So this is gonna be plus, and we have the A sub y. Take me here. A sub y gonna time what? Gonna time the 30. So that is going to be 30 A sub y. And then we have choice to compute the moment due to the moving load. Okay, you may use this each of the moment of these four loading and about B, or the best way is by using the concept of equivalent moment again, by using the own concept of equivalent of moment. What we have is we may use the F sub r, and then we take the distance of F sub r to the location of B. You understand that, right? By using the concept of equivalent moment. Let me highlight it. You may select to use this, and this is going to be what? Again, this is going to be 15 minus this one. Okay, that is going to be 15 minus same one, 0.5649. That is going to be the same as previous one. That is 14.4351 meter. So that's gonna time 14.4351, and then you will have the A sub y of, put it into your calculator, 185.25. Okay, and this one going to be 185.25 kilonewton. And then you use the what from the free body diagram of the segment. The segment of the girder. Okay, and then we do the same thing, summation of the moment. This time gonna be this one is positive, equal to 0. Let's say this one is the M1. This is for the first case, okay, for the loading pattern 1. And what we have is what the M1 gonna rotate this one, and then this one gonna rotate with the M1. So we plus 90 and time 4. However, this one gonna be in the opposite direction, so that is 185.25 gonna be equal to 185.25, and it's gonna time what? It's gonna time this distance. Okay, it's gonna time 14.4351. And now you get the first case for the M1 equal to 2315.1 kilonewton meter. So this is going to be the maximum for the first one. Okay, and next we going to put the same thing, this one, but we have another case that we going to find the center of this portion and push it into the mid span of the beam. Okay, let me do again for this second case. Let us put this one. Okay, for the second one now, let me zoom it again. Let me zoom this one again, and we have the same thing, but we will use the different. This is 90 location to put to the mid span of the beam. Okay, this is gonna be 160 kilonewton, and this is gonna be 45 kilonewton. But the same thing, we has this F sub R, and the location X bar here we have is for 1.121298 meter. So the rest of this is going to be 3. This is going to be 3 minus 1.1298, and then you're going to get this one for 1.8702 meter. And now we're going to divide this into half, and we will put this one into the center of the beam, and we will find the maximum moment for the second case. Okay, let me do the same thing. We will put this into the beam, without the beam here now. Yes, it's going to be 30 meter beams again, and we're going to divide this one by half. 1, 2, 3, 4, and 5. This is going to be half of the beam, and this is going to be 15 meter and 15 meter. So this is going to be pin and roller. Okay, and this is going to be 15 meter, and this also be 15 meter, and we gonna put this loading onto our mid span. So put this move into this one. And you may see that when we divide this into this portion, this is going to be what? This is going to be 1.8702 divided by 2. And then we get this for 0.9351. 0.9351 meter. Okay, you do the scaling again. 3 meter for 10 millimeter and 0.9351. You may get the 0.9351 times 10 divided by 3. Okay, you may guess that's about 3 millimeter. Okay, so what we have is drawing here about 3 millimeter, you get 160 kilonewton. And this one for about 3 millimeter, you get F sub R. So this is going to be 1, 2, and 3 millimeter. 1, 2, and 3 millimeter. So you get this one for 160 kilonewton. Okay, this is going to be 160 kilonewton. And this one is here. You put this one for 4 meter. You put this one for 4 meter is equivalent to about 13 millimeter. You get this one for 45 kilonewton. And then you take another 3 meter. Take about 1 meter. You get the 90. Okay, you get the 90 kilonewton. And in between this one, you get your F sub R. Okay, this is going to be 385 kilonewton. And the half of this, okay, you may put it back here, 9351 millimeter. And then you got the 90. This is going to be 4 meter. You take this one for 13 millimeter. You get this 90. That is going to be 90 kilonewton. This is 4 meter. This is going to be the second case. And if you observe this one with the previous one, they are not the same, but they are similar. Okay, and this time by using the same concept as before, the maximum moment will occur under the load that's close to the midspan. So this case, the maximum will occur about here. And if it occur about here, you got to project this. And what you have is this portion of or this segment of the beam, okay, will produce the maximum moment for the second case. This is going to be M2, and the load here going to be 160 kilonewton for 4 meter. You get this one for 45 kilonewton. And what we have, the length of this. Oh, anyway, don't forget, you're going to compute this B sub y, and this B sub y will be used here. Okay, and what is going to be this? Okay, you see this is going to be 15 meter, and this is 0.9351, so it's going to be 15 minus 0.9351, and you may get this one for equal to 14.0649 meter, and that's going to be the length here. Okay, and okay, consider the loading pattern 2. Okay, and we may say this is we consider the loading pattern 1 and consider the loading pattern 2. Let me again just take the zoom out, so we have the area to show you how to determine the M2. Okay, do the same thing. I will not put this into this. We're going to use the same one from the free body diagram of the girder AB. Okay, this time we gonna summation of the moment about A. Okay, we do the summation of the moment about A equal to 0. This time B sub y gonna rotate like this, and we have 15 times B sub y, and it's gonna equal to the F sub r, that is 385, and then the distance from the F sub r to A, if you may notice, is going to be the same distance as here. Okay, it's a 15 meter minus this is going to be 14.0649 meter. You just put this one with 14.0649 meter. Now you get the B sub y for this. This is going to be the B sub y going to equal to, this time is 180.5 kilonewton. So this one is going to be 180.5 kilonewton. Then we sum the measure of moment equal to 0 here. Okay, the shear and the 160 kilonewton will produce no moment M2. This one M2 is here, and the M2 gonna have the same moment at 45. Okay, plus 45 times 4, and it's going to equal to this one, equal to 180.5 times 14.0649 meter, and then we arrive at M2. Is M2 going to be 2,358.7 kilonewton meter. That's a little bit larger than the M pound. So therefore M absolute maximum is 2,358.7 kilonewton meter for this girder. Okay, we get this as our answer of this problem. Okay, this is the end of the demonstration of showing the problem of determining the absolute maximum shear force and the absolute maximum moment. And now you get this one is 2,358.7 for the absolute maximum moment, and this one you get is 319.2 kilonewton. So if this is the case, we obtain what we have by what? By for the absolute maximum shear force. We use the concept of maximum shear force occur at the support of the beam. Okay, it may occur at A or B, but this time we take the B. Okay, so we draw the influence line diagram of the B sub y. We get this, and then we put the loading patterns actually various loading pattern to the girder. Okay, and in this case we may have 4 of them, and by considering that we get the result of the maximum shear with the case 1 of 319.7 kilonewton. So the loading pattern is this one. Oh, sorry, we got this one, the second one, 319.2 kilonewton. This one, the blue one. Okay, and then we determine the absolute maximum moment by the concept that the maximum bending moment usually occur in the area near the midspan of the girder. That means it's maybe somewhere here. So we need to consider the loading pattern to determine F sub R, to determine X bar. Okay, and then we consider the loading pattern one, and then we do the calculation. We got 2314.41 kilonewton. Okay, and then we also do the same thing for the loading pattern 2. This time the pink, we got the center line here into the midspan of the beam, and then we get the second maximum bending moment. And since this one is the higher than this one, so this one going to be the absolute maximum moment for this case. Okay, let's you guys have a chance to study it. Okay, you have video clips. When you want to understand, you can rewind and watch it again and again. And if it's possible, I recommend you guys to stop at some point, put the number into your calculator and do it slowly. Try to develop your own skill to solving this kind of problem. Okay, that is the end of this clip.